Okay, so I think we can start. We have 30 people more or less online. It's already fast. And so we can start with Thomas Britton, the second lecture of Thomas, the third in the machine learning and AI course. So I'll let you go.
Okay. Yeah. So thanks for having me back. I guess I didn't bomb it too much last time. Today I'm going to talk a little bit more about AI, experimental calibration and control, and with kind of an emphasis on this idea of self-driving laboratories. There's been several workshops that actually have been pretty interesting, and this is more than just my project. David Lawrence is the PI. I'm co-PI, and we have several others working on various aspects of this project. So this is a larger effort. So at its basis, we should always identify the problems that we have. And running experiments is a time-consuming activity. We've all been sitting, or you will sit in taking shifts, 8 hours, exhilarating 8 hours, or 6 hours if you're lucky. It takes large amounts of time, expertise, sometimes large amount of experiments to cover the parameter space. So maybe you have to do lots of iterations. This is especially true material science, where percent doping changes the property. And so to go from 0% to 100% in fine-grained resolution may take lots of repeated experiments. Often there is a routine execution component. So there have been big steps in, like I was saying, material science, chemistry, and biology, where I ripped this from a presentation, the self-driving laboratory setup, where you have a robot that is mixing chemicals or doing analysis at the same time. This probably involves imaging of some kind. And so this has big tie-ins with robotics. So the idea is it'd be wonderful to sit back and tell the robot, figure out the problem, run the routine experiment. I'm going to go to bed. Call me when you find something interesting. And it's kind of timely, especially because this has gone all virtual. AI was actually used pretty extensively in battling COVID. Continues to be useful, I suppose, in battling COVID, not just in the transmission rates, but doing the genetic sequencing, the medical imaging, cross-referencing or correlating clinical data with outcomes. We can set policy, thanks in part to AI. So this is kind of an interesting article, and like I said last time, AI is here to stay, and we owe AI, machine learning, in part for our rapid development of the vaccine and the policies to fight it. So AI can act as a force multiplier. It's especially good at aiding in the menial. Typically, people, when doing the same repetitive task over and over and over again, they get bored. I get bored. I don't have that attention span. So we can take in robots. We can augment them to make the right actions with AI, and they can act as a force multiplier in the sense that instead of having to have a team of 12 people, you might be able to have a much smaller set of people managing an experiment, thanks in part to the automations that AI give. In Hall D, in the heart of COVID, we actually went to single person shifts. They had to set up cameras in case there was a medical emergency, other halls you needed to look because there's nobody else in the room. A little weird in the middle of the night, being alone in the counting house, taking data. But AI could fit very much into the experimental running with Hydra, which I talked about last time. This enabled people to aid in the monitoring of the data taking from anywhere in the world without having to expose themselves to possible COVID. Again, this is only made possible because there are lots of routine actions that we can kind of offload, allowing for one person to do that. And who wouldn't want an untiring optimum? if you came to my last lecture yesterday, I'm an intensely lazy person. I get tired, they don't. If we can get them to do our job, we can get more sleep. So before we can do any kind of analysis in nuclear physics, especially pretty much everywhere in physics, we have to calibrate the data. For Hall D and GluX, this often is iterative and time consuming. You could go up to months depending on the complexity of the calibrations. This detector makes a calibration change, you have to rerun, you double check. So again, related to my last lecture, all those monitoring steps where I said monitoring launches, those are tied in with this. So two different detectors may iterate on their calibration to come up with an overall optimum to use for reconstruction of the data. This is a big impediment to the analysis and thus the publication. Even sometimes experts have to diligently watch environmental factors and intervene. So I put a little anecdote here. Naomi, she's from CMU and she's working with us. She's the CDC, the Central Drift Chamber expert. And she had to call the counting house one evening and say, there's a storm approaching. We should change the run because the atmospheric pressure is changing too much. And so it'll be harder to calibrate the data. And so to take somebody who's an expert in the detector and make them also a meteorologist seems a little silly to me. So there are definitely parts of running experiments where you'll see we have gaseous volumes, PV equal nRT comes into play, and we have to change how we run to compensate for weather conditions. So particle physics in general, again, very complex, highly interconnected systems. Again, playing off of the last lecture, complex, multidimensional, correlated data. That's where AI tends to shine. That's what we have here. We have a bunch of complex detectors. They all need to work together in concert in a correlated way. Particles start at one point, end up somewhere else. Causality should be maintained. No faster than the light, was it neutrinos in that case? isn't possible. So the physics that we take is dependent on beam properties. So this involves careful control of coupled magnet systems. So you need to make sure it can go all the way around the track. And that takes coordination of the various magnet systems in the accelerator. Different detectors, you may have different detectors with specific goals. So for example, tracking detectors, you'll have calorimeters for energy deposition. You may have PID specific. And you may even have experimental setups that select for kinematics, like angular displacements and those kind of things. And so all of these are bundled. Oftentimes they can be competing. If you have the best PID, you may be giving something else up, especially in smaller experiments that may not have the resources or the room to do it all. So we needed to start small with trying to actually run or imagine running the GluX experiment autonomously, again, so I can sleep. So we broke it down. We needed to pick something that was low risk. And by that, I mean recoverable and abandonable. Yeah, that's a word. So recoverable, what I mean by that is we don't want to deploy a novel system running somebody's pacemaker. That goes wrong. You cannot recover from that. It needs to be abandonable. If it doesn't seem to be working, we need to have a fallback. We got to be able to throw the switch to off and everything is fine. We can't totally disrupt the entire experiment for the sake of trying to do this. It needs to be provable. So we need to have actually methods to show, hey, we are right. Not only is it controlling or it's calibrating, but what it's doing is helpful, it's correct. And it needs to be trustable. We need to have expected behavior. We need to be able to say, yes, it looks like it's doing the right thing. These metrics say it's doing the right thing. And we wanted something that can work alongside current systems. So deep in the back of my mind is always, can we change the paradigm? And I'll get into what that paradigm kind of is in a moment, but you can't just go from 0 to completely new ways to run experiments overnight. People tend to not trust that. That's too big of a jump. So we need to kind of parasitically sit, prove we're doing something right, and through the low risk and the trustable, maybe we can actually start changing the paradigm. So I'm going to introduce very briefly the central drift chamber, the CDC. Here's a picture of it on the right. This is the beam kind of comes in through this hole. I don't know ultimately if this was downstream or upstream. Doesn't really matter. And inside this bundle of electronics are these kind of crisscrossed straw tubes filled with gas, wire running through the middle. So they're 1.5 meters long, 1.2 meter diameter cylinder. That's the CDC. We have 3,500 nanowires that are typically kept at 2,125 voltage. And each straw is about 1.6 centimeters. It's a 50-50 argon CO2 gas mixture. And it's primarily used to detect and track charged particles with momenta greater than 0.25 GeV over C. So this detector requires 2 calibrations, the chamber gain and time to distance. The gain itself affects things like PID selection in analysis. If you're doing exclusive analyses, it's really nice knowing what you're looking at. Really nice to know that. It is sensitive to environmental conditions. I'll get into that a little bit more in a moment. Beam conditions change with the experiment as you're taking and running. So we have to monitor the beam conditions. And the gain correction factor is ultimately obtained from a Landau fit to amplitudes, a statistical distribution. You can fit it. And through that fit, we come away with our gain calibration. The time to distance is about track fitting, vertex and DEDX resolution. So we have a non-analytic function that generates 6 unique calibration constants. I will show you those in the back half when we get to time to distance. And the time to distance is really, you have these signals get produced when a particle goes through the straw. And from the timing and knowing your time to distance, you can convert that to distances. You can correlate all those distances and you can say, hey, something went that way. On the right, I'm showing the DEDX versus momentum. And you can kind of clearly see these bands, which have been labeled as the various types. So depending on which band they sit on, you get a sense of the particle identification. We also chose the CDC to target because it's got fairly simple controls. It's got high voltage, and that's it. So we have one knob to turn. Now you can argue, well, each board could have its own voltage setting, but let's not go crazy to start with. So it has one high voltage knob, and the high voltage setting affects both the gains and the time to distance. So not only do we have a calibration, that calibration is also dependent on the high voltage settings. So it's a coupled system with some feedback. It's potentially highly dimensional, especially if you're using, are we going to use reconstructed tracks? So other detectors are going to play a part. What beam properties do we need to look at? What are the environmental conditions? These are the questions that we need to answer and that AI actually might be able to help with. What variables are important in doing this? There are methods for doing that. We'll get into in a bit. And we also had a traditional method. We were already calibrating this thing. Naomi was already calibrating this thing. So we had a trusted method. We had a method that we could say, this means it's working. Can we get the AI to mimic that behavior? So our plan setting out was, can we even do the traditional calibrations? Let's see if we can make an AI that can give us the traditional calibrations. So I phrase this as, can we understand the road? So if we were going to build a self-driving vehicle, is it even possible? Well, first we have to be able to see the roadway. We need to understand the center line. There's some important basics of driving that need to be taken into account. So we need to take in various input variables, don't know what they are yet, and we're going to produce the calibration values. This seems like a supervised learning. So if you go all the way back to my first, we have an expert system. We have what we consider the truth. We're going to mimic that. That sounds like supervised learning to me. We're going to start with the gains, then go to time to distance. Gains are easier, much easier than time to distance. And then hopefully we can leverage those gain predictions for controls, because a high voltage and the calibrations, they're coupled. So if we can accurately predict the gains, we may be able to target a specific gain and change the high voltage instead. So the gains we started with, they're simple, okay? It's just a fit to a Landau. So it's just you take in some amount of data, you take in some input variables, and you predict a number. We already knew that pressure is a primary driver. Naomi, our detector expert, said pressure is going to be in there. She had to make a call about a storm. And it's also related to board currents. And basically it comes down to, these are gas-filled tubes. A gas-filled tube, a gas, PV equals nRT. So what the gas is, the temperature of the gas, and the pressure, the volume, the straw you consider to be rigid. And that gives us kind of a starting point in the physics of control and calibration. It's definitely smaller in dimensionality. Again, one control, we have high voltage. So assuming it works, we have a nice, tidy little play area to see if this is even possible. So the gains, conventionally, the CDC operates at this 2125 voltage. The calibrations are fine-tuned in an offline setting. So we take the data, we're close enough. Then we go through this iteration afterwards in the following days, weeks, months. The current method is relatively slow, requiring lots of iterations. And the time scale to complete all of it is a few months to make sure everything is proper. So the AI, the idea is to maintain a consistent detector response to the changing environment and experimental conditions just by changing that high voltage. So we have this AI sitting on the high voltage knob, and it's going to be turning it, hopefully to produce calibration constants online, because we're targeting it. So the image that I have is, we take in some input values, the beam properties like the flux, atmospheric pressure. AI takes these input variables and it produces high voltage values. CCDB is our calibration constant database values. So for example, the CDC gain is also going to be produced. So we're going to produce recommended high voltage to get out to our target gain, but also what the target gain happens to be. Because we can't constantly turn the knob. We have to take some data each setting. So there's a little bit of kind of coarse adjustment, fine adjustment paired up. So what are our considerations? This isn't a machine learning approach, an AI approach. So how are we going to train the model? What data do we need? Again, first lecture, that's what that was all about, is same questions. How are we going to train the model? Do we have the needed data for inference? So that's a big one. Are we going to have to go out and re-instrument part of the CDC to get the needed data? Is that data going to be formatted correctly? That's important. Very, very important. How do we integrate it with the current operations? Remember, we don't want to just completely displace the previous methods. We want to be alongside, aiding, not truly disrupting. And we want as little human input as necessary. That was my kicker. I don't want to have to deal with it. Once we set it up, let's just walk away. That would be our goal. So feature importance. Oftentimes I've found that when you're approaching a new problem, you use the spaghetti approach. You see what sticks. You throw lots of variables at the input, and then you basically ask the resulting models, assuming they do well enough, okay, which variables did you use? And there's lots of different ways to kind of get at this. So L1 regularization, very simple. It's really only good for a small number of variables, especially linearly correlated variables. I'm not going to get way into it. There are the Shapley values. That's what we used. We also tried these Gini importance parameters. There's a whole host of them. You're free to Google them. They all work in various different scenarios, and oftentimes you can't ab initio know which one. So you try a few and you say, oh, they're all agreeing that the most important 3 variables are X, Y, and Z. Let's do that. And you get these kind of cool plots, which are giving us an indication on each data set, the effect on the output of each of the variables. It's underlabeled in this, but you can see somebody's hovering over the net amp. And by getting the output, you can see, well, these variables are trying to push the number higher. These are pushing it down. This is the biggest contributor because it's the length, and so on. So when finding what sticks, when we first started this, on the left was our input variables. Yeah, you can't read it. I can't read it. You shouldn't read it. But one thing that stands out is there's only blue kind of up here. So we went in and we said, okay, forget all the ones that it's not using. It's confusing the situation. And we get down to this middle one. You can see the blue bar kind of goes down here. But this stuff isn't really doing anything. So we cull again. And we end up with a much smaller subset of variables we can use for a model. I'm not going to get into what exactly each variable means. I'll be talking in general terms very soon about that. One thing you have to take when you're doing this feature importance, do you really need the variable? Maybe there's multiple ways to do it. And so reconstruction for us takes a long time. We can't do it online yet. Maybe with some tracking stuff, which hopefully you heard about yesterday, there may be avenues to make the tracking or parts of the tracking fast enough that you can start doing it online, and then maybe you can use those variables, but we couldn't. So we decided to do it only with EPICS data. EPICS is it's a kind of an online system. I forget what the acronym stands for off the top of my head. It's the thing that records all the variables and control parameters. It's used in industry all over the place. It's pretty old, and it's basically a database of values. So temperature over time, and pressures over time, and beam currents over time, and high voltage settings over time, and those kind of things. And it turns out that is completely doable, which is great. We don't have to try to lobby or work on reconstruction. We can just do it with EPICS data. Are things correlated? So you have a bunch of variables that you say are important. If you're using both Fahrenheit and Celsius, that's silly. That's probably harming the model more than it's helping, because they're directly correlated to each other. So you only want the smallest unique subset of variables. And you can make plots of the variables to look for correlations. And that's what I'm kind of illustrating on the right. You can set out all these variables. You can say which ones are highly correlated. Do we need both of them? Why or why not? So on and so on. You really want to seek the minimal set of features. Still want to be robust. What does robust mean? Depends on your situation. And some redundancy might be okay, but nothing as silly as too directly computable from each other. So we have data which we're extracting from, there it is, experimental physics industrial control system, EPICS. And our initial features are generated from the atmospheric pressure, that's the P. Gas temperature, that's the T, and PV equals an RT. And the current drawn from the CDC high voltage boards. That kind of came out of nowhere. It's a good proxy for us for the beam condition. So basically the rates in the CDC is related to beam intensity and probably focus and all those things. We can bundle it into an engineered feature. It turns out current drawn from the CDC high voltage actually works as a pretty good proxy for that. And all of these are readily available during the experimental taking. So here's pressure, temperature, and high voltage board current over time. Boom, right there, we just ask epochs for the values. Awesome. Then we ended up using a Gaussian process, which I know I didn't say anything yesterday about this. It's kind of the most awkward to explain, so I ignored it. No, you're trying to get to figure out the probability distributions of various models or various functions that fit a set of points. So you're trying to figure out both the covariance matrix and the line of best fit, if you will, at the same time. It's suited to small data sets. If you get into the nitty gritty, it becomes readily apparent. Large data sets, it's not really feasible to do. Hey, we have small data sets. We don't have that many runs. 1,000, half 1,000 is 500-ish. It's not much. It provides uncertainty quantification, which if you start getting into AI and you go to any workshop at the DOE, one of the challenges which always ends up on the list is uncertainty quantification. I remember in grad school, early results, I just did central value. I hadn't worked out all the error correction. I got pulled aside by my advisor and he goes, never, ever, ever go to a group working meeting and present anything without error bars. I was like, I didn't have them right. I mean, I could have put the statistical, but they would have been really small. It didn't. He goes, never do it. The error is often the most important quantity you have. So it's really nice if we can kind of get that to come along for the ride. This was implemented in scikit-learn. So previous lecture was all about TensorFlow, Keras. This is another common and useful package in machine learning. So early results. Oh God, big table. Basically what you gather from this is some methods don't generalize well over the data sets. So we take data in blocks. We have run periods here at the lab. And usually the run periods to have different kind of fundamental conditions. We're going to run it higher beam current, lower beam current. We're going to do this special physics. And so a lot of the models weren't good at figuring out something that worked for everything. And this makes some sense with discrete running conditions that you may do better just by targeting. And that's what these dates are. But it turns out that the Gaussian process with 5 features, it does very, very well. And so this one is the one you can kind of compare this line to this line, which I put the arrow at, to see what the variance is between runs. So that's what we ended up going with. And here is, over time, as we train, the top one is, I forget, it's like 2 epochs in. It's very early in the training process. And you can see it's starting to hit more of the points, but the errors are quite big. And as you add in more data, so it's data driven. When you don't have much data, bigger errors. When you add in all of the data, that's all these red points, you get a much better line of best fit, and you have to squint really hard. There's error bars on it because the uncertainty comes. And this makes sense. You'd get bigger errors towards the edge. This one is based on atmospheric pressure only. Why? Because visualizing things in like 4 dimensions is hard. Also, this is the most important variable. So it made more sense to show it this way. But everything seems to be working how we would expect. So we have now a method, a machine learning method that does a pretty good job. It's only based on a few input variables that we have at runtime through epochs. Awesome. So I think I think we're good with gains. Let's talk a little bit about time to distance. So the CDC is ultimately a tracking detector. So we're interested in the wear of particles predominantly. Look, proton went that way. That's what we would love to say. So we take the signals and we understand how fast the electrons drift the wire. If you get into how drift chambers work, you have high voltage on that wire. And as the particle liberates electrons, they get sucked to the wire. And when you get the signals, it's correlated to where the particle was when these electrons were being liberated. So it's high voltage dependent. It's gas dependent. So both the gas mixture and also PV equal RT. It's a good approximation. So what I have here on the right, just so you get an idea, is a plot of the drift radius, because you only get how far away from the wire. It's running on the center. So how far away from that wire you are, expected versus ideal. So if you're on the wire, it's the same, and you get more uncertain as you get further out, which makes sense. These are, yes, for a bunch of different voltages, just showing there are differences between the pressure, so the purple and the blue, as well as voltage. You can see the separation pretty clearly. So the current calibration method produces 6 unique calibration constants. It turns out there's an added wrinkle, which is kind of annoying. Gravity, darn you, gravity. We have these straw tubes. We said they're rigid. Not actually 100% true. So we can actually look at the straw deformation, which is these kind of fudge factors, if you will. Hopefully Naomi didn't hear that. It's like a fudge factor for which straw has how much deformation. You have to correct the time to distance calculation for each one. And this is a plot of showing both the drift time and the straw deformation value for all the straws. And you can kind of see these bands. They line up on this gradation, which is good. At its core, we're trying to find A1, A2, B1, B2, C1, C2. That's 6. And these will give us our time to distance values. Coming from this distance based on time, it's the function. You can plug it in, do the math. I don't think it's as important. It's here for reference. This one has many more difficulties. So we have 6 parameters. Game, we had 1. There's actually ambiguities in sign. If I flip back, you can work out that individual A1s and A2s, B1s and B2s, how they play together. You can modify signs and still have it come out right. So when we used a neural net with a custom loss to bake in the prior equations, remember me talking before, custom loss functions, we actually saw these signs shifting. So some of them that we think should be positive should be negative. Often in physics, as everybody knows, you take a square root, you get plus or minus. One of those values is nonsensical, you drop it. But in some of these cases, it doesn't matter, you just pick one. So that can cause problems in training though, as something is headed towards a negative, but the loss may be getting higher, depending on how the math exactly works out, So we ended up switching to a Gaussian process regression again. And we did it in 2 ways. This is primarily Diana's work. Thank you, Diana. You use a cascading method, which I show over on the right. It's read kind of right to left. In other words, you take the epochs variables, hopefully, you predict A1, you use A1 to predict A2 with the epochs variables, you use A1 and A2 with the epochs variables to predict B1, and so on until you cascade through all of them. This comes from an understanding of some correlations that exist between them. And you can get, there's added problems with doing the cascade. And you can also simplify by just doing one Gaussian process regression per parameter. So A1 has its own, B1 has its own, C1 has its own, and so on. And what the nice thing about this is we already had experience with it working in games, and we've just reduced the problem. So what I'm showing here, 2018 and 2020 are run periods. And we looked at the mean % difference compared to the traditional method, as well as the max % difference compared to the traditional method. And you can see that universally, Gaussian process regression did better. Yay, better. You can also see that there is a significant difference. There is differences between 2018 and 2020. it's not uniform. We don't maintain the same error, mean percent error. So I gave a description here. The neural net was 4 layers, 16 nodes, different activation functions. Remember I was talking about that before. 5 input features, 6 output values. And we made this double integral custom loss function. The GPR, the kernel, uses this radial basis function and white noise. So you kind of smear it out, which gives you, helps with the errors, I believe. And you get 6 predictions, 1 for each calibration constant. And you can see in the additional uncertainty, we have more, in addition to the uncertainty. So one reason to use Gaussian progression is we get those uncertainties for free. It's part of the whole method. So in addition to that, we have more accurate predictions. So very nice. So we have one method that actually turns out to work for both. And here is just an example of the standard deviations across the various test runs we analyzed in 2020 for the A1 parameter. So I just throw this up. This was kind of our baseline result. This is the model that we use going forward. Hopefully through hearing this, it may all make sense, but hopefully there's a nagging thought in your head that says, but what if the traditional isn't right? I mean, it's pretty good, but how do we know it's the best? Do we trust it? Yeah, we do. Naomi's good. We trust it. We have published measurements. We trust that our detector is right. So I'm not questioning that. But we should question, is it the best? Because we can have a disagreement between the AI and traditional methods. The AI could be producing better physics. It could be acceptable in the traditional, but we don't know. We need to answer that, maybe. So one question I have is how much difference is there in physics outcomes with errors in say, the gain values or each of the time to distance? What does it really mean to be off? Because, right, I'm sitting here talking about max differences in that drift function. How much does 0.093 really affect things? On a cliff, could be a lot. On a flat line, not at all. What does it really mean? It's difficult. Usually it's not a singular value. We don't have a number that we can say, this means better physics because of those competing outcomes that I was talking about earlier. So you have a bunch of different metrics, matrices, each with different priorities. Oh, we get better K-on PID, but we lose some momentum resolution, or vice versa. I'm just making something up. So again, what are our actions? So if we're going to take what we've done for our AI and we're going to put it in a control system. This is the fun part. This is the fun part. We know we got it to give us our calibrations. Let's make it drive itself. CDC only has only one high voltage. So I don't want to oversell. We took this on purpose. We took this approach on purpose because we had one knob to change. So then the question is, how do we interact with the control? It turns out that actually the CDC has this epochs variable for the high voltage set point. If the voltage is on, it goes to the set point because it's being read from epochs. So if we just change the set point, it'll change the voltage. And the rate is about 10 volts a second. It's not linear, but it's on par with 10 volts a second. So even if we are self-driving it and we say, oh, go up 5 volts, it's not instantaneous. Do we need to worry about that, for example, while it's ramping up or down? Does that affect things? So our goal for control was to modify that voltage to stabilize the gains. You don't have to do gains calibration if it's always the same value, or if it gives you that kind of fine feature change, fine sanding, if you will, coarse sandpaper versus fine. So traditionally, the input variables are fluctuating, the voltage is held. And so the constants and the gains are, the V is held constant, so the gains fluctuate. That was kind of what I was showing in that early plot. Or you can, in principle, fluctuate the voltage with the input variables and produce a stable gain. So you're playing the voltage and the kind of gas properties due to the environment off of each other. Okay, they wouldn't let us like implement a system. Yeehaw! Let's see if it works with beam on. Would have been nice. Would have been nice, but okay, fine. So we'll take a second. We'll be a little bit more step by step, and we're going to use the cosmics to gain confidence. Remember, trustable. People tend to trust people. You don't trust a self-driving car the first time it goes out. But if you say, my team has been working for 6 years, making sure everything is fine, you tend to have a little bit more confidence that it might work. There's also higher stakes with beam on. It's just, people get touchy when you start messing with detectors with beam on. I get it. I get it. So we're going to use cosmics. So we want to, again, to underscore this, we want to create a smart detector system which can adapt to its environments and produce self-calibrated data. Or, okay, at least reduce the iterations. Maybe instead of months of iterating, we can do some of this one polish iteration traditionally based off of starting values. So the system that we're going to create should be able to adequately control the detector, no user input. That's key to me. No user input. If somebody has to take the wheel, it's not self-driving. So maybe we'll put a human approval step in there. Like, I'm going to change the voltage. Do you want me to? It makes people feel safe. Or maybe we just don't do that and we just do it anyways, which is what I lobbied for. Because if we constantly feel like the only way we can run this is if somebody is constantly hitting yes on it, we're not really self-driving. And I need this system to be able to update arbitrarily fast. Because ultimately what I want for things like streaming readout, I don't know if there's been any lectures or talks talking about streaming readout in the hugs. Streaming readout is kind of a different way to look at data collection. And as much as you can do as close to the detector, the better. So we need to be able to keep up arbitrarily fast. So our cosmic test, we split our CDC into 2 halves. It's like a saw and just cut, no. We just subdivided the detector and put some straws on orange on the left side. I think in looking beam downstream, or is it beam upstream? It doesn't matter. And the blue side is the other side. We're going to leave one at the fixed high voltage, and we're going to let the AI control the other one. And then we're going to compare the results from the rain of cosmics. So the AI we set up is going to update the high voltage every 5 minutes. And it's going to be completely autonomous. It's going to be completely autonomous. I don't want to have to touch it. I'm going to set it up, I'm going to start it, and I'm going to walk away. This was good too. Some of our collaborators went on vacation during this test. Tori, who was off camera, and myself were the ones that really were here and had to monitor the situation. And it doesn't sound fun to watch this thing. So let's just make it drive itself so we don't have to. And we should see the AI system stabilize the gains. So here's kind of a schematic. We have the epochs variables. We have a control system, which is sitting in a loop, reading those data, that input data, doing the analysis. We built some modular functions. And this is kind of important. And I wanted to take a second. When you're building these systems, oftentimes people have an urge to build monolithic systems that handle all your workflow in one script. Yay, it does everything. It's better often to have modules. So as Diana improves a model, she can change as necessary these modules, and my control system rarely has to care. We sat down a few times. We came up with what we called a verbal contract. This is the input data and how I'm going to hand it to you. It's format. You hand me back, oh, okay, a dictionary of outputs labeled with these keys. Great, perfect. We're going to do that. So she can change the models basically on the fly. And her job is going to be loading the model stuff, model parameters, the specific model, everything necessary to run inference, to run that prediction. And I don't have to worry about it as I'm building the controls system for this. teamwork. So the control system itself is on the fly configurable. So in this loop pass, it's polling. So this loop rate is configurable. What we call the recommendation scale. How often do you want to actually recommend the voltages to change? All the default values for all the parameters. What happens if epochs goes down in a certain variable? What do you do when you start driving off the road? The control mask, how much of the CDC do you want to control? When running in production, it'll be all, but now it needed to be left side, right side, this one specific channel. It needs to have a look back time. The engineered features, like brush this under the rug. I'm sorry, I'm a terrible person. I brushed it away. Those input variables that we ended up using are not just pure variables. They tend to be like mean being current. And as soon as you say mean, you have to have over what period looking back. All the other control parameters are configurable on the fly, which is great. I don't have to take the system down, tweak some hard-coded thing, bring it back up. I can just change a config file and wait one poll cycle, and then I'm done. Here's the money plot. It's so awesome. What do we have? This is the gain constant on the top. I'll give you one guess. Which side is AI controlled and which side is not? Okay, I'm not going to make you guess, because if you guess wrong, it's going to look real bad. The orange was a fixed voltage. The blue was AI controlled voltage. The blue is rock solid. There's a little blip here. This blip, I can explain this blip away. It's better than this. The temperature in the hall, the gas temperature, was not in our training data. It was close by, but our training data came from real physics runs. The hall is closed. Nobody's opening the ramp doors. You know, all that kind of stuff. And so we pretended, we lied to our AI, and we said, it's in the data, it's close enough to this value, just treat it as that value. Once things warmed up, that line is when we turned on and we said, okay, read the real temperature. And you can see it's flat. It is flat. And we were very fortunate to have this big change, a storm rolled through. And our autonomous system was able to adequately attune that parameter to stabilize the gain. So if we could answer accurately, how big of a change in gain does it matter? This variation could well, and I think it is, I think we did some looking, is well within the physics tolerance, which means you could just basically set a line, say, this is what we think the gain should be at. And in principle, you wouldn't have to do gain calibrations ever again. You just control the high voltage every 5 minutes during the run. Excuse me. And it works. This is so awesome. I got my sleep. And then collaborators came back and like, how's it going? And it's like, oh, I don't know. Fine. So success. We've gotten a control system running near real time that is controlling autonomously the high voltage setting of an actual detector sitting in the hull, and it's actually doing something good. I can only imagine it's similar to how Tesla engineers felt when it completed one loop around the track without crashing in simulation. It's very nice. So what's the next steps? Big success. Other systems, give us other systems. In and out of GlueX. So we're looking at like the forward drift chamber, because we did decently with the drift chamber. Hopefully the same techniques can be applied. Our barrel calorimeter, which sits around our CDC, it's a calorimeter. That would be slightly different. And the TOF, which is downstream and is useful for PID. And the one reason we would love to start with we would love to do another GlueX detector, is we want to move towards interoperability. So that loop of calibrations, I changed my calibrations, the reconstruction has changed. Everybody has reconstruction again. Oh, because you've changed this, we need to change the parameters here. Okay, run reconstruction. Oh, it turns out that that was too high. Maybe you need to bump this down. It'd be nice to have a system that sat above everything, looking and constantly maneuvering holistically the entire detector systems. Because after all, we really want to optimize the physics results, not the gains. We really want better physics. So we want to take this and disrupt data taking. No, not disrupt data taking. We want to start changing the paradigm. So I want to move to a mode of operation where this idea of run is just a human construct. It's just easy to talk to people about it, but more streaming readout like. So you turn it on, you walk away, it gathers data, you do quick analyses with hopefully online reconstruction. And so each event that you get is perfectly calibrated. Detectors are operating continuously in a changing experimental environment, and everything is perfectly in balance and harmony. So perhaps those conditions themselves are optimized. After all, we get beam from the accelerator, and we judge that beam based off ultimately the quality of the physics we get or our estimation of it. So maybe we can ask for change different beams to optimize the data taking. So going way back to that first picture, that robot is taking various quantities, mixing them, analyzing them. Maybe something. Maybe you can already have data reconstructed online. That saves a lot of time. Maybe the paper is written for you. That'd be great. So once the paradigm is changed, we can move towards self-driving. There's a lot of synergy here with other AI tech. In order to drive a car by itself, you need to have a control system that has the proper policy to react to the environment. I'll say reinforcement learning. But you also need a camera that can detect stop signs, classify objects as pedestrians. So there's going to be synergy with other AI technologies in this process. I'm pretty sure what Gaggeek told you about yesterday will fit into this picture, this dream picture. The experts only are going to engage at this high level. And the routine operations are delegated to the machines themselves. So I can do what? Sleep and not have to. And we need some kind of protocol for interoperability. So operational data made for AI, formatted for AI, made by AI for AI. That's another common trope in a lot of these workshops going on at the DOE, which is how do we make sure things are instrumented such that we can build AI for it? What data does AI need to do a good job? So we're going to set our sights beyond experimental border. There are connections with the accelerator. Actually, I'm not an accelerator physicist at all, but I know I have to call them up sometimes and tell them the beam's bad. We need a better beam. Maybe we can not have to make that phone call and it just kind of all happens because we really want to optimize that physics output, whatever that happens to be. It's very, I know, gray. I'm not sure what it means either. So the accelerators are, in my mind, I'm going to get flack for this. They are a means to an end. If we didn't have the physics experiments, fast moving particles, it's fun, I get it. I'm guessing it would be harder to actually build accelerators just for the sake of building accelerators. And those tunings required for physics. Detector configurations that are dependent on beam properties. Depending on what the accelerator can give you, you might change your experiment. So imagine holistically managing both the experiment and the beam in real time. Not you though, the robots. Let the robots do it. So I don't have time. I'm almost at my time. I put 3 links just dancing over the surface. A lot of work going on, a lot of really good work. In Slack, they're using Gaussian process models. There it is again, to optimize beam tunings for their experiment. So can they get a better beam to the experiment? SNS, the spallation neutron source, has projects going on in detecting beam faults and also component degradation. When do you send techs into the tunnel to replace something before it explodes? And so a lot of the maintenance stuff could be very expensive, time consuming, lost beam time, precious, precious beam time. Even here at the lab, Chris Tennant has done some great work with RF cavity fault diagnosis. So not only who failed first, why? And then maybe once you can identify those, maybe you can change some running properties. That's what the errant beam is also looking at, is maybe you can finagle the control settings to avoid the problem if you can predict the problem early enough. So I'll leave you with the visions for the future as I see it. I want to design with AI, so I don't have to do it all alone, for AI. So we can build machines that do it all on its own. So I'm talking Bayesian optimization for detectors. There's some work going on for the EIC of how do we perfectly optimize the physics we want to do, the detector configurations and setup. Where do we put detector components? Systems instrumented for AI. So standard protocols. I think we need standard protocols for being able to talk between systems. We need automated diagnostics, hopefully self-correcting. I think a problem's coming. If I drop the voltage for a bit for whatever, I won't degrade, I won't have a fault, and then I can bring it back up as needed to optimally do it. Self-documenting, because I mean, I'm not gonna speak for anybody else. I always document exactly what I do all the time. I'm lying again. And I want quicker to physics. So in my mind, if we have this dream system continually running, you can start talking about co-modeling. And by that, I mean hypothesis generation. You can do generic anomaly detection, say, these are interesting events, keep them. That's like your trigger work. How do you explain? You might be able to slip some AI that can look at the body of work that we've done and aid in interpreting new data. A lot of interesting work, kind of sci-fi work going on there. And that puts me basically at my time. So thank you. I'll take questions if there are any.
Let's thank Thomas. I do. They are clapping.
Okay.
Online. You don't see that. You open the list of participants already, yes?
Yeah.
Okay. If you have a question, just raise your hand and unmute yourself, and we can hear you from here. Yeah, you have a question.
Go ahead and unmute Aaron, I think it is.
So once you've picked a machine learning model, but that model has some parameters like the number of layers in neural nets, how do you go about optimizing that parameter? Is it mostly just looking at, the true positives and true negatives and false positives and false negatives and seeing what gives you the best results on the testing data?
Yeah, so great question. For those that maybe didn't hear it or didn't hear it well, basically the question is, how do we go about, so I'd slipped in, thought I could get it by you, but no, I didn't. Right here, 4 layers, why 4? 16 nodes per layer, why 16? How do we do this? It's something called hyperparameter optimization. And you can do an entire lecture series on hyperparameter optimization, but suffice it to say, you try a bunch of different ones. And there are sophisticated methods. There's something called grid search that's the easiest to understand. Let's see if 3, 4, or 5 layers work. Let's see if 4, 8, 16 nodes are better per layer. And these 2 activation functions. And then you try every combination. And then in this case, you look at some measure of, because this is regression, you could look at false positives, false negatives. You could look at the overall loss value, which I talked about last time. And then you find the best one. And then you can quibble about which is best. The one that's generalized better, the one that gets more results within some parameter. What does that mean? And you can go down a rabbit hole. Essentially what happened is, I think Diana did some hyperband, another method of hyperparameter optimization based on experience. Basically, it starts with get something in the ballpark, figure out why it's in the ballpark, try things related to it, and then depending on your metric, choosing the best one, whatever that happens to be. Oftentimes, people present their best nothing else. I try to give you a little bit more of a nitty-gritty. It doesn't work easily. It's not for free. Hopefully that answered your question at least enough that points you in some directions you can dive into. It's philosophically very interesting stuff. We have other questions.
There's Sarah. You can go on.
Yep.
You said you were looking at new systems for choosing to apply machine learning and designing new detectors that you can apply machine learning to. When you're looking at new applications, like what is the base set that you look for that you're like, yes, machine learning here?
I'm going to give you my off-the-cuff kind of snarky answer, and then I'll get into it more. My off-the-cuff snarky answer is the thing I don't want to do anymore. The better answer is it would be wonderful to choose a detector that is different enough, so calorimetry instead of drift chambers, for example, but still simple enough that we aren't saying we got a one knob device to work, we're going to do a 100 knob device. In general, high dimensional connected coupled systems, which basically is any one of them. So at some level, we sat there and we had hours-long discussions about what to target next. And often it was like, maybe we could just apply what we did before. We could prove that that technique works in more places. Great. Maybe we should do something completely different. Maybe we should get to, well, that one is too hard to control, or that one we don't have the same kind of detector expert buy-in, or that one has never been calibrated, so we have nothing really to compare to. Maybe it will help, maybe it won't. And we kind of hit around asking people, detector experts, what problems do you have? Oh, it's really annoying when our PMTs behave this way. Do you understand why they behave this way? It has something to do with these features. Good idea. We can maybe do something with that. If you go to a detector expert and they say, it's kind of annoying having to turn this crank, but it's directly calculated. We have an analytic equation that just gives us the answer after one turn. Probably not gonna attack that next because it's already solved. So I think I come at it from more of a sociological, what is annoying experts? Can AI be applied to it? I look for multidimensional, highly coupled. And I, on a personal note, moonshot stuff is kind of fun too. So sometimes going into something with no expectation of success is the best. You got to do it safely. So. All right.
I don't see any other questions so far, at least.
And that's, I think, my hour because we started a touch late.
Yeah, you don't have anything to add, I will stop here the session, and we will meet in 15 minutes. And thank you again, Thomas, for the nice lectures.
Thank you. Thanks for the audience dealing with this. It's a little different yesterday.
Well, thank you very much. It was very nice.
Okay.